As you can see, the subject of my presentation today is the development and evaluation of alternative aviation fuels. I'm first going to begin by defining what I mean by the term of an alternative or a synthetic aviation fuel. I'm going to discuss many of the factors that are motivating the development and use of alternative aviation fuels and the corresponding criteria that have to be satisfied in order to pursue these. And I'm also going to discuss some operational performance requirements that are unique to when you use a fuel for aviation applications. Once I've done this, I want to then take the opportunity to highlight some areas where researchers at UD have made significant contributions to the development, use, and certification of alternative fuels for aviation applications. A lot of that work was done in collaboration with researchers from the Air Force Research Lab at Wright-Patterson Air Force Base, and without their collaboration and sponsorship, a lot of our contributions wouldn't have been possible. Before I begin, I want to take the opportunity to thank the STARS Committee to speak here today, the Research Institute and UD for their continued support of our work, and for you in the audience of having enough interest in investing your time in today's talk. So simply stated, an alternative, or you'll hear me use the term synthetic fuel, is a fuel that's derived from non-petroleum sources or feedstocks. Gasoline, diesel, jet fuel that you're typically used to are derived from conventional or heavy crude oils or non-conventional petroleum feedstocks like tar or oil sands. An alternative fuel could be derived from other fossil sources like the liquefaction of coal or natural gas to liquid fuels, or biological feedstocks like plants, algae, or animal waste. Now, this latter category is probably what most of you in the room think of when you hear the term of an alternative fuel. Now, there's several motivating factors that are driving the interest in the development and use of alternative fuels for aviation applications, and these can be broadly classified into four primary categories, as recently summarized by Heilman and Stratton in a publication. I'm showing these four categories here in a Venn diagram, and you'll see this consistently with the criteria that I show on the next slide, because we need the right combination of these factors in order to have the motivation to pursue the use of these fuels. Now, for simplicity, the impact or the magnitude of each of these factors are drawn to be identical, but they can vary substantially depending upon many factors like geographical location where you're producing these fuels. First and foremost, a fuel has to be economically sustainable in order for us to pursue it. Some of us in the room are old enough to remember the oil embargo in the early 70s. When petroleum products were pulled from the US market, there was a lot of investment and interest in alternative fuel development. But once those crude products went back in, a lot of that investment and interest waned. There's obviously environmental sustainability motivating the use of these fuels. In particular, many of you probably think of the potential impact of CO2 and greenhouse gas emissions, but it's not only when we use these fuels and burn them, but what's produced or emitted as we're producing these potential fuels. There's other air quality impacts to consider, like the fugitive emissions during the production and burning of the fuels. And an often considered resource that's not considered is the water intensity of your processes, how much water is needed and the quality of the water. There's energy supply diversity motivating our interest. You've heard the president say in multiple speeches, we want energy independence in this country. We want to become less dependent on a single or combination of foreign countries for our liquid transportation fuel needs. So that's driving our interest here. This is difficult just due to the sheer magnitude of the volumes of fuels that are used in this country, but any diversification helps. And the last driving force or motivation is the competition for these resources. If a feedstock or a source can be used to produce an aviation fuel, it can probably also be used for ground transportation. It can be used to generate electricity or heat. So what's the best use of that resource, not only from an economic standpoint, but from an environmental and a sustainability standpoint? So as you would expect, the criteria in which we evaluate a potential fuel echo these motivations very closely. A fuel is only going to be able to be pursued and become sustainable if it's economically viable. This can be complicated by the fact that policy and incentives can affect prices that go into this, like tax incentives that are given for ethanol production for gasoline use. Another limiting factor for the aviation industry is that any alternative fuel that's developed has to be fully compatible with existing infrastructure and aircraft, just due to the longevity of these systems that are used. So we basically term that they have to be drop-in fuels compatible with the petroleum-derived fuels. There's global climate change and air quality impacts that we have to take into account in our criteria. You've heard this in maybe life cycle analysis or life cycle emissions, and you'll hear the term well to wake. Everything from getting that feedstock out of the ground or growing it all the way to what we use it. What's the impact there? It'll be impacted by such factors as where the carbon's coming from, if it's a fossil carbon or biological source, the emissions when it's used and such. A fuel has to be compatible with both legacy and future aircraft. As I said before, in the economic side, it has to be able to be used in existing infrastructure and aircraft. It has to meet specification fuel requirements. These are the properties that when a fuel producer makes a fuel, we evaluate certain properties that have to be satisfied before it can be sold in the open market. It also has to satisfy what we term fit-for-purpose properties, which I'll talk about in a couple slides down the road. And then the other criteria we have to think about is our resource impact. We'd like to have feedstocks that have large production potential, but we got to account for the resources that are going to go into those and the best use of that resource. Now, I mentioned jet fuels at the beginning of this talk have some unique performance and operational requirements when we use them. And this is due to the nature of how they're used on these systems. I've listed a few of these requirements here. A jet fuel has to have high energy density and specific energy due to the volume limited fuel tanks you have on an aircraft. You basically want to make your flight without having to stop and refuel as you're traveling. We have to have many safety of operation due to the conservative nature of air travel. This includes being able to safely handle these fuels on ground and when we're putting them into aircraft. We have to have good thermal stability characteristics. We basically don't want to foul our fuel passages or nozzles in the combustors during flight. And we have to have good fluid properties, especially at the very low temperatures that can be encountered at high altitude flight. And there's a myriad of other properties and characteristics we need, including appropriate fluid properties and compatibility with airframe and fuel system components. So with this in mind, a lot of the fuels or chemistries that you've probably heard of for alternative fuels, biodiesel, alcohols like ethanol and butanol, liquefied natural gas, and liquid hydrogen, are not suitable for aircraft use because of many of these concerns. They're much more suitable and can be implemented in ground transportation applications. With respect to aviation fuels, the types of chemistry and the compounds that are going to be produced and be viable to be used on aircraft are going to look and smell a lot like the chemical classes and compounds that you have in petroleum-derived fuel. Branched and linear saturated hydrocarbons, cyclic hydrocarbons, and aromatics. But a big key here is understanding which classes do you want and which classes are beneficial to be implemented within aircraft applications. There's a myriad of feedstocks and processes that you can use to produce an alternative fuel. Commonality to all these is that they're typically going to have to require hydrogen addition at some point to remove heteroatoms like oxygen, sulfur, nitrogen. And they're right now going to have to be blended with petroleum-derived fuels for use. A complication for aviation fuels is that right now these processes can only produce a blend feedstock that can go into petroleum-derived fuel, and each pathway and fuel has to be approved individually. Thus far, there's been 3 pathways that have been approved for use in commercial and military aircraft. This includes gasification of carbon sources to produce synthetic paraffinic kerosenes, conversion of triglycerides to hydroprocessed esters and fatty acids, and the conversion of sugars to synthetic isoparaffins. To assist in improving the speed and efficiency in which we can get these fuels to market and get them approved, there's been a standard processes developed to provide a framework for the certification and approval of new chemistries. These can be divided into 2 basic areas. There's the research and development stages, where we characterize the physical and chemical properties of these fuels and understand how they're going to potentially impact use on an aircraft. And then there's certification activities, which could include full-scale engine testing, airframe testing, and review and approval. Within this process, these upstream research efforts, especially correlating and understanding property to performance relationships, are critical because we can define and learn a lot about the potential viability of an alternative fuel or an alternative fuel chemistry by requiring small volumes and doing relatively inexpensive tests till we scale up. With AFRL colleagues, we've developed a lot of expertise improving these property to performance relationships, and you see this term again, fit for purpose property, so I might as well define it. For a fit for purpose property, what we mean with that term is it's a property inherent to a petroleum-derived fuel that's not controlled by specification. So as a petroleum-derived fuel is developed, as I mentioned, there are certain properties that have to be evaluated to be able to sell that on the open market. Now those properties were defined such that as long as those primary properties were satisfied, secondary, tertiary operational requirements of these fuels would be inherently solved. But this isn't guaranteed when we introduce alternative fuel chemistries into use. It's not feasible to directly evaluate all of these characteristics during the procurement, but as the end user, you want to make sure you're getting the performance that you need. So this is a very busy slide, but these are just some of the fit-for-purpose characteristics that you require for operation and safe operation of an aviation fuel that aren't explicitly tested for every time we evaluate it. These include characterizing the chemistry and potential impurities, bulk physical properties and performance, especially how they vary with temperature due to the wide ranges of temperatures experienced during application. There's properties related to safe handling of fueling and fuel transportation, toxicity, material compatibility with fuel system components and airframe components, combustion performance and stability, and other operational issues. So these are areas where we've developed a lot of expertise and really helped to advance the knowledge with both DoD and Air Force colleagues, but other OEMs, airframe components, engine manufacturers and such. So I want to touch on some of those areas and just give you a highlight of some of the accomplishments that we've made. But before I do that, I want to make mention of a very important occurrence. About 10 years ago, the Air Force made the strategic decision to certify all of their aircraft fleet for operation with blend of a petroleum and a synthetically derived fuel. And this was a major undertaking. It involved activity from the research effort all the way up to engine and aircraft OEMs to flight certification. A lot of this work was done and initiated out of AFRL with our direct support and contributions, including understanding property to performance relationships and how physical properties vary with blend ratios. We did a lot of the initial combustion evaluations to make sure the fuel would burn satisfactorily. One of the things we observed with that was the potential for reduced sooting or particulate matter emissions with these fuels. We supported extended durability and on-wing testing on the B-52, the first aircraft platform certified for alternative fuel use, by performing emissions measurements. And I mention this because this really has catalyzed the interest both from a government and military perspective, but more importantly, a commercial perspective to pursue and approve and certify alternative fuel use for aviation applications. Now, as far as some specific examples of areas where researchers at UD have made substantial contributions, I've mentioned a few times the relationships of property to performance. How does specific chemistry affect our operational needs? Now, there's conventional techniques that exist for characterizing fuel chemistry, but for the level of detail that we need for some of these new chemistries, conventional techniques won't suffice. So researchers like Rich Strebick, Zach West, and Linda Schaefer with us are developing and improving analytical techniques such as multidimensional gas chromatography. What that allows us to do is separate these fuels all the way down to the individual molecular level, which gives us a much better opportunity to correlate the composition to performance. Obviously, a need that you have to have from these fuels is efficient and effective combustion performance and thrust. You want to be able to fly your aircraft. We've done a lot of work with aircraft OEMs and AFRL, understanding how the fuel chemistry will affect the combustion performance. We've done work using research combustors both at AFRL and here on base. We've worked with AFRL and engine manufacturers like GE Aviation to develop advanced capabilities like this elevated pressure combustor developed by Scott Stauffer and colleagues, where we can then use this to evaluate and do robust R&D regarding the effect of fuel chemistry on performance and large-scale engines. And the R&D that's been performed is provide critical information to the aircraft OEMs that these fuels will or can have the potential to provide the required performance. So just kind of give you an idea of the type of insight that we can get on a fuel. I'm showing here testing we did with an atmospheric combustor operated with petroleum-derived military fuel. We see good stability in the flame, but downstream we can see sooting and particulate matter production, basically the soot that would come out of the back of the engine. Operated with the synthetic paraffinic fuel, we have good stability in the flame and good characteristics, but you see a substantial reduction in that downstream emissions. This is beneficial because it shows you may have the potential benefit of reducing particulate matter or soot emissions that come out of these engines both on ground and during flight. With that in mind, with AFRL under Edwin Corcoran's leadership and having team members like Chris Klingshirn and Joe Mance, we've developed advanced capabilities to be able to fully characterize gaseous and particulate matter emissions, both in the laboratory, but also on wing and on aircraft engines. And these aircraft engines have been deployed around the country. GE Aviation here, various government facilities, Pratt & Whitney, but we're very proud of the capabilities that we've developed and we've been able to use to characterize potential environmental impacts of these fuels, including the first emissions evaluations of full-scale alternative fuel blends on both B-52 and C-17 aircraft. And I think overall, it's fair to say we're a national leader in this work that we're very proud of. Another area where we need to have good property performance relationships is compatibility with fuel system components and aircraft engine components. This is a photograph of emissions testing we did with a NASA DC-8 engine. We fueled this aircraft and the engine with a synthetic fuel. We came back the next morning and fuel was dripping all under the wing and all on the ground. And obviously you wouldn't want this happening before your flight, but more importantly during your flight. So understanding and identifying what are critical characteristics of these fuels that we need to be able to have to ensure that we get good material compatibility is critical. Researchers like John Graham here at UDRI are developing advanced capabilities where they actually incorporate real flight system hardware like these fuel system couplings, and they can expose fuels and different fuel chemistries to in-flight simulated conditions and very well predict and correlate the ultimate performance. He's also improving ASTM techniques like taking this large volume, long duration seal swell test and being able to do it with much smaller amounts of fuel and shorter durations to improve that iterative procedure. An area where you may not know of concern for hydrocarbons is the potential for contamination in these systems. And this can be detrimental because we can have degradation of these materials, and we can also form biofilms that can plug filters and impede fuel flow. We've been doing a lot of work with AFRL where we're looking at the impact and the understanding of the property to performance relationships, either beneficial or detrimental to the biocontamination and biogrowth within these systems. And the last slide I want to mention, this is in a different division that I work with at UDRI. This is coming out of the Energy Technologies and Materials Division under Sidhu's leadership with researchers like Moshan Khandawala. They're looking at using algae for carbon capture, storage, and then subsequent cultivation, and they get to a point where they could potentially produce a fuel that could be used for ground or aviation applications. And this is an area where we collaborate and interact directly with them to better understand what are the potentials of these fuels and try to put it all together. So just to kind of summarize, I appreciate everybody bearing with me through this talk. Hopefully, at least, at the minimum, I've impressed on you that development of alternative fuel candidates and chemistries is complex. Many factors are required to have a viable fuel candidate, and you have to certify and approve these fuels before you can use them. A major area where you can make a lot of economic benefit and a lot of technological improvements is improving the understanding of property to performance relationships, where we have done and continue to do a lot of work. We're very proud at UDRI and the university for the major contributions we've made in this area that have provided the basis for the currently approved fuels, but also future fuel formulations. And this is evident by our inclusion in the recently established FAA Center of Excellence for Alt Fuels in the Environment, which one of the primary goals of that is to develop improved and faster approval processes to get these fuels to market. And in general, the potential exists for more environmentally friendly and economically stable fuels. So to sum up, if there's one thing you take away with this talk is that I'm solely responsible for all of the good work that's come from Alt Fuels. But that's as far from the truth as possible. I couldn't even begin to do this slide justice. There's been so many individuals within UDRI and UD, including Steve Zabarnik, our current division head, and Dilip Balal, our previous leader in this area. Lots and lots of AFRL colleagues, Tim Edwards, Bill Harrison, primary leads over there, government agencies, fuel producers and suppliers, aircraft engine OEMs, private industry that have all contributed this, and it's truly a team effort to bring this to work. I unfortunately won't be retiring if Apple calls me because we'd have to split everything throughout. And we're very appreciative and proud of our long-term research and professional relationship with AFRL that's helped us develop our world-class expertise in aviation fuel chemistry and engineering.
Thank you, Matt.